All right, guys. So this is part two of the video series. We're going through the 2015 international exam, the FRQ, the free response, and we've gone through questions one and questions two, and now we're moving on to question three. Remember, questions one, two, and three are the longer questions. They're each worth 10 points. So we've already gone through 20 points of the test. There's only 26 more points to go. So 10 more points on question three, and then we'll get into the 4-point questions. Okay, so let's go into question three. All right. So what I want you to notice here is, they give us the structure, big organic compounds. And remember, for structure, they might be asking about, shape. They might be asked about hybridization. And especially when they give us structures like this, remember, there's two lone pairs on that oxygen. They didn't draw them. Okay, it's understood that they're there. So that, if they asked about this bond angle, it's not 180, it's 109, right? There's two lone pairs on this oxygen. So if they asked about the hybridization of this oxygen, it's sp2. It's not just S because there's only one domain. There's actually three domains around that oxygen. So that's something to be careful. And then, also like look at, that bond angle is not 180. That bond angle would be 120 because this carbon is trigonal planar. So just little things like that. And then, the main thing to look out for is, most of this compound is just a hydrocarbon. And there's this big functional group on the end. So we do have a functional group that allows us for hydrogen bonding. But if we thought about like a mixture of these molecules all combined together, there'd only be kind of like one site where hydrogen bonding could take place, and the rest of it would be kind of London dispersion forces. Whereas this molecule we have, that's a place where we could have hydrogen bonding, that's a place where we could have hydrogen bonding, that's a place where we could have hydrogen bonding. So probably a lot more hydrogen bonding going on in this molecule versus that molecule. So if it came to boiling point, I would probably go with sucrose over the lauric acid. Just kind of things to look out for when given something like this. So it gives us the structures of these two compounds and says which compound, lauric acid or sucrose, is more soluble in water. Okay, so this question is asking more of, it's not about boiling points or strength of IMFs. It's about similar IMFs. So remember, like dissolves like. So they're both polar, and they're both have hydrogen bonding. So they're both similar in terms of water, like dissolves like, but the sucrose has way more places where hydrogen bonding can occur. So I would expect the sucrose to be more soluble. All right, let's see what the scoring guide tells us. All right. Yeah, sucrose is more soluble than lauric acid. Stronger interactions occur between sucrose and water molecules due to the greater capacity of hydrogen bonding. As a result, a larger number of OH groups in sucrose, right? Okay, so there we go. So although lauric acid molecules have one site for hydrogen bonding, the long hydrogen carbon chain causes London dispersion to be the predominant yet weaker interaction with water molecules. Okay, there you go. So just kind of comparing the two. This has hydrogen bonding, this has hydrogen bonding, but this has more sites for hydrogen bonding, so it's going to end up being more water soluble. All right. All right, assume that a 1.5 gram sample of lauric acid is combusted and all of the heat energy transferred to 325 gram water sample at 25 degrees Celsius. Calculate the final temperature of the water if the molar heat of combustion of lauric acid is negative 37 kilojoules per gram. So notice this said kilojoules per gram. I underlined this for an important reason, right? Usually, like I just said molar heat of combustion. It's not the molar heat of combustion. Molar heat of combustion would have to be kilojoules per mole. It's the delta H of combustion in kilojoules per gram. So if you take this and you multiply it by grams, which they gave you, 1.5 grams, that would give you kilojoules, all right? Now, all we're gonna do is take that total energy by burning 1.5 grams of this and put it in a Q equals MCAT equation. It'll be our Q value, but we have to be careful, right? This is the specific heat capacity of water, and it's in joules. And if I do 1.5 times 37, that's going to give me kilojoules. And so I got to then multiply by 1,000 before I put that into Q equals MCAT. All right. So what I would do is do 1.5 times 37 times 1,000 to get joules, plug that in for my Q, and I would just solve for delta T. I wouldn't solve for final temperature. I would just say delta T equals Q divided by MC. and I would calculate the change in temperature, and whatever that value came out to be, then I would add it to the initial temperature, and that would give me my final temperature. All right. So let's see what they did here. Yeah, so they did the same thing I suggested. So we get 56 kilojoules of energy because we did 1.5 grams times 37 kilojoules per gram. Grams cancel out, that gives us kilojoules. Times 1,000, that's where that 56,000 joules comes in. So we're doing Q equals MCAP, but we're solving for delta T. So we find that there's a delta T in 41 Kelvin, but a delta T in 41 Kelvin is a delta T in 40 is delta T 41 Celsius. A change in 1 Kelvin is the same change in 1 degree Celsius, okay? So all we would have to do is add 41 to the initial temperature, and that would give us our final temperature, 66. All right. In an attempt to determine the molar heat of combustion of lauric acid experimentally, a student takes 1.5 grams of lauric acid in a ceramic dish underneath a can made of aluminum containing 325 grams of water at 25 degrees Celsius. The student ignites the sample of the lauric acid, which with a match, and records the highest temperature reached by the water. The experiment is repeated using a can of the same mass, but this time the can is made of copper. The specific capacity of copper is 0.39. The specific capacity of aluminum is 0.9. So aluminum has a higher heat capacity. Will the final temperature of the water in the can made of copper be greater than, less than, or equal to the final can? So because copper has a lower heat capacity, the copper is not going to absorb as much heat as the aluminum would. So in the copper can, water would end up absorbing more heat. So the final temperature of the water in the copper can would be greater. So greater in copper because it has a lower heat capacity. And yeah, the temperature will be greater in the can made of copper since copper has a lower specific heat capacity. All right. In both experiments, it is observed that the measured final temperature of the water was less than the final temperature calculated in part B. Identify one source. So remember, we never take account energy loss to the environment. So that's what I would say. Possible answers include heat loss to the environment. There you go. Heat is transferred to the thermometer. Thermometer is kind of part of the environment because it's not a part of the reaction. So that's kind of the same thing. Incomplete combustion. That would be a good one. That's not one we really talk about too much, but yeah, I think the main thing is, hey, we didn't account for any heat loss to the calorimeter. We didn't account for any heat loss to the environment. We didn't count heat loss to the thermometer. Okay. All right. Part D, the experiment described above is repeated using 1.5 sample of sucrose. The combustion reaction of sucrose is here. Even though the delta G for the combustion of the sucrose in air is negative, that is a very low delta G. That's a very, 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 if you calculated the equilibrium constant for this, it would be ridiculous. It would be like your calculator would say error because the number's so big. The combustion reaction does not take place unless ignited. Explain. Remember, if a reaction is very thermodynamically favored but isn't happening, it's because it has a high activation energy. Let's see what the scoring guy said. The reaction has a high activation energy. The ignition source provides the energy for the molecules. There you go. All right. Predict the sign of delta S for the reaction and justify our reaction. So remember, we have a solid and 12 gas molecules on this side, and then over here we got 23 gas particles. So a lot more gas particles on the product side. The products are more random, more disordered. So entropy is going to increase, so a positive delta S. And the main thing is, 12 particles of gas to 23 particles of gas. We can kind of ignore the solid there. Yeah, there are 23 moles of gaseous products for every 12 moles of gaseous reactant. There you go. All right. All right, that was all of question 3. Now, let's move on to question 4. Now, understand, question 4 is only worth, and let me scroll down. Question 4 is A, B, and C. Okay, and that's it. So question 4 has 3 things. So one of these, A, B, and C, is going to be worth 2 points, and the rest is just going to be worth 1 point because there's only 4 points we can get here. Okay. So the boiling points and dipole moments and polarizabilities of the 3 hydrogen halides are given in the table above. So here are our boiling points. Based on the data table, what type of intermolecular forces among the molecules HCl, HBr, and HI is able to account for the trend in boiling point. Okay, so they're all polar with all dipole moments, meaning they're all polar. Okay, HCl is the most polar because the bigger electronegativity difference than HBr than HI. So they all have dipole-dipole interactions. But, right, HI has the weaker dipole-dipole interaction because it has the weaker dipole moment, less polar. But it has the highest boiling point. And, right, remember, everything has London dispersion. So the key difference here, they all have dipole-dipole interactions, but what's putting HI over the edge? Iodine's a much bigger, greater London dispersion, much bigger cloud. So let's go here. London dispersion forces. There you go. Okay. And if I go too fast, guys, maybe pause your screen so you can read the whole thing. But I'm just kind of giving you kind of a gist overview of the test here. Okay. Based on the data table, a student predicts the boiling point of HF should be 174. Obviously, they're going to be wrong because what can HF do? HF can hydrogen bond. Okay. But when they looked at the boiling point, it's actually higher than all of them. Okay, explain the failure, and it's because HF has hydrogen bonding, right? HF has hydrogen bonding, okay? And then it says representation of 5 molecules of HBr in the liquid state are over here. In the box, draw the representation in vaporized. So remember, just they separate from each other, okay? They're still HBr, so you still got to have the H attached to the Br. But now they're going to be occupying the full container in random spots, right? All right, let's see what their scoring guide did. Yeah, there we go. Pretty. How did mine go? Almost. Pretty close. All right. Maybe I work for College Board. All right, so that's question 4. Let's go to question 5. All right, so again, remember okay. So here the dots I drew in the dots. Like none of the bonds were written here. They just had H, C, O, C, H, 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 and O, like O here. So they didn't have any of the bonds written, and they didn't have any of the lone pairs. So we had to fill in the dot structure. Now it didn't say anything about formal charge, so there could be possible answers to this. But the main thing is that we have to know how many dots we need. Right, so obviously there has to be at least one bond between all these things. Carbon will not have any lone pairs on it. That's something to know. Usually if oxygen's in the middle of a carbon chain, it ends up with 2 lone pairs on it in single bonds. And if you have a random oxygen coming off of a carbon, that's usually when you have the double bond O and the 2 lone pairs, right? So this is, the ether group. This is a carbonyl group. When you combine them, that's what an ester is, but you don't need to know that. That's not a thing. And we didn't need to know that for this, okay? All right. So if we look at, that was just filling in the dot structure. Okay, so if we look at what's going on here, it says 0.02 moles of methyl malate into a previously evacuated 1 liter container, so that means moles equals molarity if we need to know that. The pressure is measured to be 0.74 atmospheres. When the experiment is repeated with 0.02 moles of ethanoic acid instead of the methyl methanate, the measured pressure is lower, okay? The lower pressure of the ethanoic acid is due to this reaction. So it's looking 2 gas particles becoming 1 gas particle, so the pressure goes down. Assume that the equilibrium has been reached when 50% of the ethanoic acid molecules have reacted. Calculate the total pressure in the vessel at equilibrium at 450 Kelvin. I'm thinking make a rice chart for these 2 questions because it's equilibrium and it'll help us organize our information. All right. So we started with 0.02 moles per liter. Remember, putting in a rice chart, you want to make this molarity, but because our volume was 1 liter, our moles that we started with are equal to molarity. So initial, before any of the ethanoic acid reacts, okay, 0.02 molar and 0 molar, it'll be minus 2x plus 2x. And then remember, they told us 50% of the ethanoic acid reacts, so we'll have half of it remaining. Okay, so we can figure out what x is. X equals 0.005. So now we know that this is going to be 0.01, and this is going to be 0.005. Okay. And oops, let's go back. What's the question? Ask, calculate the total pressure. So what we could do is take our total moles of gas, right? Take our total moles of gas and plug it into Pivner. So we have 0.01 moles plus 0.005 moles. That's where this is, and we would just solve for our pressure. So we found total moles, and we plug it into Pivner to find our pressure, 0.55 atmospheres. Okay, and then here it says calculate, whoops, back up to the question. It says calculate the equilibrium constant for the reaction, but it's Kp. So it would be the partial pressure of this over the partial pressure of that squared. So remember, we can do our mole ratio to figure out the Kp. So this is our total pressure. Now, we calculated 0.55 instead of, because we did it this way. We did it the ideal gas law way. So I use 0.55 in mine. But you would just be 2/3 of this pressure is the ethanol, and 1/3 of that pressure is the whatever this is, the combined methanol or ethanoic acid. And so those would be our pressures. We plug them into the Kp expression, and we solve for Kp. All right. All right, so I'll stop this video for this because I'm running out of time. My next class is going to start. So what I want you to do, I'll come back later with the part 3, and that'll go over the last 2 questions, question 6 and question 7. All right.